Welcome back to module 1 of the course Time Dependent Quantum Chemistry. We have been discussing vibrational superposition state, and we have shown that for cos equals cos function equals 1, which means that at t equals 0 at the beginning of the superposition, we have proved that the density will be localized or more at a particular point, which is we are defining as B point in the space. And we will look at what will happen next if we make the cos value 0. And if we make the cos value 0, it means that I have t equals pi by 2 h cut divided by delta E 1 0. So I have this psi xt density equals alpha by pi to the power half e to the power minus alpha x square plus 4 alpha cube divided by pi x square e to the power minus alpha x square. So I have these two functions adding, and if we add these two functions, what we have is that all would be positive. And adding these two functions, it means that I have all are square basically. So I do not have, I have this function, then I had another function, but it is now squared. That's why it will not have any phase like this, negative phase like this. So, and if we add them together, we finally get this, which means that the density has now come, maximum density has come to this middle point, which is defined by A at this time. Similarly, if we continue and use -1 value, which means that t equals now pi h cut by delta E 1 0, then what I get is that xt total density square is now just going to be e to the power minus alpha x square by 2 minus 4 alpha cube divided by pi to the power 1 by 4 x e to the power minus alpha x square by 2 whole square. It suggests that first we have to subtract these two wave functions. So now we are subtracting these two wave function. That's why we have changed the phase. Previously here the phase was positive and negative here. Now we have negative here, positive here, and we are subtracting. If we subtract it, then what will happen? This two needs to be added now, and if we add them, then clearly this portion of the wave function will be magnified, and this portion will be destructively interfering, and that's why we have now total density moved to, maximum density has moved to the position C. So what we see from this time dependent change in the density, the position of the atom, we see that the densities is changing from B position to A position to C, and again it will be oscillatory. So C will come back to A and B, and this is the way densities is changing, and that's exactly manifesting the molecular vibration. So coherence has now allowed to observe the change in density as a function of time, which can be experimentally observed. The same frequency, with the same frequency of the molecular vibration. But if it was staying at V equals 0 state, that was a stationary state, there is no way we could observe this change in density or this frequency of vibration. So coherence has a beautiful effect in the experiment, and one can make use of the coherence to observe certain thing which cannot be observed if it is in stationary state. So far we have talked about quantum superposition, and there is a in optics often we talk about superposition, and by taking superposition of optical wave, that is the plane wave, we can create the pulse, and often we discuss that pulse, and it is important to introduce that immediately, because very soon the superposition state, quantum superposition state, which is nothing but a wave packet, we'll be discussing wave packet, and getting an idea from optical interference can help us understand better what does it mean by the wave packet and its propagation. Light is a dual nature. It has dual nature. When light exhibits wave nature, it propagates as an electromagnetic wave. On the other hand, when light is particle, we consider it's propagating as a particle. So life has a dual character. The kind of character we are considering here is the wave character of light. So light as a wave we have to see, and the moment we see light as a wave, we express its electric field in this following form. Here also, just like wave function, we see that there is a phase factor, temporal and spatial phase factor, which is nothing but e to the power I theta kind of an expression, phase factor. And once we see that phase factor, we understand that it's changing the phase as a function of time all the time. This is complex notation. In real notation, one can express as cos omega naught t minus kz. This is the real part, and this is an oscillatory part. So maximum field strength is oscillating as a function of space and time. So this is a picture which is taken at a time, let's say t. Freeze that time. At a particular time, suddenly if we think that electromagnetic wave propagating through space, and at a particular time I would like to know how the field strengths are as a function of distance, we see that at this distance field strength is maximum, at this distance field strength is 0, at this distance field strength is maximum but in the opposite direction, at this distance field strength is 0, and so on. Like this way field strengths distributions are. Similar pattern can be observed for time. At a particular point of space, if I try to plot how electric field is changing as a function of time, this is also similar way. Different time at a particular point, its field strength is changing, and that's the manifestation. We are talking about electric field because generally electromagnetic wave has both electric field and magnetic fields, but magnetic field strength is weaker than electric field, and that's why we are neglecting magnetic field oscillation here. We are only considering the electric field oscillation. Now when something is propagating, there is a very easier way to consider e to the power. So this phase factor is nothing but cos omega t, and cos within bracket everything should be angle. This is going to be an angle. So what we can do is that when electromagnetic wave is propagating in linear space, we can represent its propagation in a circular dial. That can be used, and that's the way this angle, the phase angle, will be defined. For an example, here we are starting from here at this point, and then when we reach, so basically from here to here, when we reach here, we make an advancement, linear advancement, but angular advancement made by pi by 2. From here to here, when we go there in this linear scale, we make another angle advancement which is pi, and when we come here from this point to this point, we make 3 by 2 pi the angular advancement. On the other hand, when we come back here, it is the 2 pi angular advancement we create. So this linear motion, this linear advancement and angular advancement, they are correlated. And how it is correlated, that is something which I am going to show here. This kz is the term which is controlling the linear advancement. So if I advance z plus lambda wavelength, total wavelength, then angular advancement would be 2 pi plus kz. So previously it was kz, now I have linear advancement z plus lambda, that will give me angular advancement kz plus 2 pi. So it gives me k lambda equals 2 pi, or k equals 2 pi by lambda. K equals 2 pi by lambda. These are the relations which are important for all these plane waves. And as I mentioned before, that omega naught t minus kz, this part is called the phase of the electric field, and that is very important. Phase is very important physical quantity. It's important physical quantity because if you think about this phase, red one, color represented by the red color, we see that this red color is repeating after a certain distance, again is repeating, which means that, let's say I am in a space, light is propagating through the medium. When light propagates through the medium, its electric field is oscillating in the medium, and we have somehow managed to find out a red color light which will be turned on whenever the electric field is maximum, which means that I am collecting the phase this one and this one. So red color will be blink, after certain time red color blink, after certain time red color blink. And question is, with what velocity this whole thing is propagating? In order to find out, we can find out by taking the constant phase front. You see the phase front here is repeating, so it's constant phase front, and if I take the constant phase front, it means that the time derivative of that phase omega naught t, total phase is omega naught t minus kz, it is actually time derivative of the phase, that is going to be 0, or in other words dz dt, that is the velocity, that is called phase velocity, velocity of the constant phase front, velocity of constant phase front, that is Vp equals nothing but omega naught by k. So this is the way we define the velocity. This is an important concept we have developed, how we define the velocity of a plane wave or light. Plane wave of the velocity is related to the phase, that is the phase given here. So I've been telling that phase is an important concept. Phase has information of the velocity. How do you get that velocity information? It is the constant phase front velocity. That's why the phase is taken to be constant, and with respect to time, derivative of a constant is going to be always 0, and that's the way we find out the phase velocity. So this concept will be used very soon in the superposition. Optical superposition, which creates the pulse, that is the pulse, localized electromagnetic energy. So this is called localized electromagnetic energy. Wave packet, on the other hand, it is the localized particle wave. So these are the two, conceptually different, but they have very close similarity. And how do you create that? We create optical superposition by considering two two slightly different frequency components, they are interfering with each other, and there are places where they will be interfering constructively, there are places where they will be destructively interfering. In the end, the final pulse should look like this, a pulse which is localized electromagnetic energy in space. And when we look at this, the optical pulse creation will be able to we will be able to define it, because electric field, total electric field, will be defined in following way. Total electric field is nothing but E naught e to the power I omega 1 t minus k1 z plus E naught e to the power I omega 2 t minus k2 z. Two electric fields, two plane wave propagating along the same direction, but they have slightly different frequency, and how the total electric field is changing. So this is equivalent to creating a pulse like this. Is creating a pulse. So we are considering only two electric fields, and if we define now omega average equals omega 1 plus omega 2 divided by 2, k average equals k1 plus k2 divided by 2, and delta omega, difference in omega between interfering waves, is omega 1 minus omega 2 divided by 2, and difference in k equals k1 minus k2 by 2. If we do that, then I'll be able to plug that in here, and I'll be able to express this total electric field as E naught e to the power I omega average t plus delta omega t minus k average z minus delta k z plus E naught e to the power I omega average t minus delta omega t minus k average z plus delta kz. If we simplify it to some extent, we'll be able to get this E naught e to the power I omega average t minus k average z multiplied by e to the power I delta omega t minus delta k z plus e to the power minus I delta omega t minus delta kz. This is complex conjugate of each one, so I'll be able to write down 2 e to the power I omega average t minus k average z into cos delta omega t minus delta k z. So, and if we take the real part of it, real of this E total, then we get 2 E naught cos omega average t minus k average z into cos delta omega t minus delta kz. We get two different oscillation. One is slowly varying, another one is fast varying component. Omega average is higher frequency, so fast varying component very quickly is changing. Delta omega, I told you that the frequencies are very small difference, so delta omega is going to be very small, and that's why this is going to be a slow varying component, this is going to be a fast varying component. So there are two the variations we see, and that's exactly is shown here. This one is slowly varying component, which is defining the field envelope. But this one is fast varying component, which is defining the resultant the carrier wave. This is called carrier wave. So this part is carrier wave, and this slow part is defining the envelope part. And if we look at these two, then it is clear that for a pulse I have, because two different phases, the phase is defined by this part and this part, so two different phases will be defining two different velocities. Again, velocity will be defined. So phase velocity of the pulse will be defined by the velocity of the constant phase front of fast varying component. How can I get that? Clearly, I had phase omega average t minus k average z. This is the phase. I take the first derivative to be 0. If I take first derivative, constant phase front will repeat. That's why first derivative is 0. It is the velocity of the constant phase front. So if I take that, then I get the phase velocity. On the other hand, group velocity of the pulse. What does it mean? It means that the velocity of the constant phase front of the envelope or slowly varying component. For that, I will take the first derivative of this one, this phase, to be 0, and we get this group velocity. So what does it mean? Fast velocity and group velocity is that when I have a pulse, I have an envelope function, slowly varying envelope function, and I have the fast varying components, which is called the carrier wave. Both are actually propagating through the medium. Question is, what is the velocity of this envelope function and what is the velocity of this carrier wave? These two components are different, and these two components will have independent velocities. So sometimes it may happen that they are together, they have the same velocity. Sometimes it may so happen that they have different velocity. That's why one is proceeding quickly than the other. So I will plot this pulse one more time. This oscillation is moving through the phase velocity, but this one, which is part of the envelope function, going through group velocity. Collectively, what is the velocity they are moving forward? Individual average component, how they are moving forward. So these are the two components. It is very important, and we will be using this kind of concepts very soon in wave packet dynamics in the later different modules. We have come to the end of this module. In this module, we have introduced time dependence Schrodinger equation. We have tried to understand the meaning of wave function. We have tried to understand what we observe experimentally, that is the density which we observe, and in order to observe the density, I need to see time dependent density, which is nothing but the superposition state. So if a particle staying in a stationary state, its wave function is time dependent, but its density is not time dependent, and that's why it is stationary state. In order to observe quantum dynamics, I need to have superposition state. And for observing superposition state, one key information, the time versus delta E, this is inversely proportional to each other. So if I create a superposition state or vibrational superposition state, because vibrational spacing is very small, its time would be much longer than the electronic superposition state. Electronic superposition state, delta E is much larger, and that's why it's much faster time scale of the density oscillation we should observe. So with this, we will end this module. we will continue discussion of time dependent quantum chemistry in next module.